Hello everyone. So in our presentation today, uh, we will present about the foundational principles and design of our project building a medical diagnosis ecosystem using first-order logic. Our core objective is to develop an ecosystem capable of diagnosing the medical condition. So now the critical question is, why did we choose first order logic or FOL for this ecosystem? We will explore it justly, but the simple answer is its power in representing complex factual knowledge and reasoning. To understand our project, let's first review the fundamentals of an expert system. An expert system is a computer program that attempts to simulate the knowledge and reasoning ability of a human expert. In our case, a physician. It consists of three main components. First, knowledge base. This stores the domain expertise, essentially the medical facts and rules. For example, if symptom A and symptom B are present, then EDC is likely. Number two is the inference engine. This is the brain that applies the rules in the correct way to specific specific patient data to reach a conclusion or diagnosis. Number three is user interface. The point of interaction for the user or the patient or the doctor. So how the expert system simulates a medical expert. A doctor use their knowledge base uh, to analyze a patient symptoms, input data, and draw a conclusion. Inference engine. Our system mimics this process by using its rules stored in LOL to logically infer a diagnosis from the report symptoms. So let's deep dive in first order logic. The power of our system comes from the formal language we use. First order logic, FOL, is essential because it allows us for powerful cross representation. The core concept of FOL first is predicate, predicate relationship or properties. For example, here has system cost of favor, then it is aspirin or the treatment given treatment. Variables stand symbols that stand for any object in the domain. We use them with quantifier. The logical connected and for the multiple conditions or for alternative condition and then to define a rule. The quantifiers this allows us to make statements about rules or of objects. The universal quantifier for all the existent existential quantifier that exists. So here is the RL example. This translates to for all patient X. If X has cough and X has fever, then X has a flu. So why RL is ideal for diagnosis. Uh, FOL is perfectly suited for medical diagnosis for two main reasons. First, completeness and soundness. It guarantees that if a conclusion diagnosis is logically entailed by the correct medical facts, the system can derive it. Number two is the explicit rules. It allows us to define a clear rules that directly match to establish the medical knowledge. And our implementation choice the current. To implement the logical inference, we choose the current library because current is powerful, elegant, and declarative logic programming library in Python that makes implementing the LLM-based inference engine highly efficient and reliable. In conclusion, our project leverages for formal power of first-order logic to build a reliable and robust medical diagnostic system, slowly simulating the reasoning of a human physician.
Hello, everyone. Today, let's take a step back and imagine the following. You walked into a clinic, you tell the doctor, I have a fever, I'm coughing, and instantly the doctor says, you might have influenza. So, how does that happen? It's not a magic, it's logic. And today, I will show you how we can build a small part of that logic inside the computer using first order logic and an elegant Python library called Karen. So what we're building is essentially a mini doctor or an expert system that reasons about diseases based on symptoms. So let's dive in. So first, what's Karen? So normally when we write Python code, we do something like this. If this, else that, and maybe some nested condition. But Karen asks us to think differently. So instead of telling the computer how to solve a problem step by step, we tell it what the relationships are, and Karen figure out the how. So Karen is not a machine learning, not neural networks, not statistic, and definitely no training and no data set. Karen is simply pure logic. And it lets us write things like if the patient has a fever and a cough, so the patient may have influenza. And then Karen takes those rules and, well, thinks for us. In a sense, Karen turns Python into a tiny, elegant logic engine. Tools from Karen. Here's a key difference from Karen that we will use. So the relation, think of it as a table, a list of facts about the world. Facts, this is how we insert knowledge into the table. Var, a placeholder, the things we want to solve for. Counter, a way of expressing logical rules like ands and ors. Equi, a way to say two values must be equal. And run, this is the engine. It searches through all our rules and facts to find valid solution. And together, these elements are like Lego blocks. We stack them together to build a reasoning system. The vocabulary. Before a computer can reason about anything, we need to tell it which words it's allowed to use. So first, we defined a list of symptoms like fever, cough, nausea, shortness of breath, and a list of diseases like influenza, COVID-19, asthma, etc. These are just string pieces of text, but they form the vocabulary of our medical word, and Karen will only reason about the words we give it. Now, let's say a patient tells us, I have a fever and a cough. So how do we teach this fact to our system? We use this function, returning user symptoms into facts. So line by line, first we create a new relation, initially empty, and then for each symptom, we create a pairs like this, P1 equal to patient 1 with fever and patient 1 with cough. Then we load these pairs into the relation using facts. So the relations initially empty, it will become a list of each pairs. And in English, the facts we just added are something like this. So has symptom, patient 1 with fever, and has symptom, patient 1 with cough. And this is literally how we teach the system what the patient is experiencing. And at this point, we have knowledge but no reasoning yet. And that comes next, the knowledge base. Now we get into the heart of this project. The knowledge base is a list of medical rules written in first-order logic style and implemented using coder in Karen. So a rule like this, which means if the patient has fever and a cough, so the disease is influenza. And inside the code, we have a whole list of rules. And this means a disease is possible if any of these rules is satisfied. This is powerful because it allows us to express overlapping symptoms. So for example, in this case, we have cough and short breath is pneumonia, but cough and short breath is also asthma. So Karen basically will return both diseases when those symptoms appear. And that's exactly how a real doctor thinks. Maybe these symptoms could mean A or B. The inferences engine. Now let's bring everything together. Here's the key function, the diagnose with Karen. We have a symptom list, which is basically the symptoms that the user will type in our system. And the output of this functions could be a list of possible disease. So step number 1, we assigned a patient. We called it P1. It is a label and it's optional. Step number 2, we build the fact. We called the build symptom relation to insert facts like has symptom P1 fever. Step number 3, we create a logical variable. This is the blank we want Karen to fill in. And step number 4, we run the inferences. So this code means the 0 means give me all solutions. So if you just want one solution only, you just type 1. And Karen check each rule in the knowledge base. And if it's satisfied, it will basically take it in the disease var variable. And any rule that matches the patient's symptoms produce a valid disease and we will save into the possible disease. And step number 5, we remove the duplicates because multiple rules might infer the same disease. And then finally, we return the list. And this becomes our diagnosis. So in short, a user type in the symptoms into our system, and we have the facts, and we also have the rules. So we will code Karen to reasoning this, and then it will return the possible disease to the patient. And now for a demonstration.
Now I will demonstrate how our medical diagnostic expert system work in practice. So we build the user interface using the radio. So the interaction is so simple and intuitive. You can see in here. The user only needs to select the symptoms from the list, and the system will automatically infer the possible diseases based on our first-order logic knowledge base. Now we have some tests with the system. We have case 1 with the symptom fever and the cough. Then I submit it, and the possible diagnosis is influenza. It means if a patient has a fever and a cough, then the patient may have the influenza. So the system correctly returned the influenza as a diagnosis And this so that in inference engine is working directly from our logical rules. We move to the case 2. We have the cough and the short breath. These two symptoms, right, appear in more than one disease in our knowledge base. Is pneumonia and asthma. So the system outputs demonstrate our support for overlapping symptoms and multiple possible conclusions. Next, we have case 3 is sneezing, runny nose, and itchy eyes. Sneezing, itchy eyes, and runny nose. We have the allergic rhinitis. This confirms that the rule involving multiple symptoms also work correctly. And as you can see, the system responds instantly, and all these conclusions come directly from the first order logic rules defined in knowledge base and executed using the current logic programming library. Next, we talk about the strength of the system. Our system has several strengths. First, the user interface is so simple and intuitive. User don't need to type anything. They only need to choose the symptoms, which make the demo very user-friendly. And second, the interference engine is built with the Karen, a logic programming library that naturally supports the first-order logic through the predicates, variable, and rule-based reasoning. Third, we have implement 10 diseases and multiple overlapping rules. This satisfies the project requirement, and also the system return multiple diagnoses where the symptom match more than one disease. Finally, the system run fast and produce clear and readable results. But however, we have some limitation for this system. First, our rules currently have an equal weight. The system does not calculate how likely the disease is. It's only check if the symptom match the logical rule. Second, we do not incorporate real medical data or severity levels included. Third, the system only handles a single patient at a time, and it relies entirely on manually written rules. So thank you for your attention.